In this video, we're going to look at something called Sp2 hybridization. A good example is this C2H4 molecule. So let's draw a Lewis structure, a basic Lewis structure. The two carbons are probably going in the center because I know they make more bonds than a hydrogen. So most likely, we'd put the carbons in the middle with their 4 valence electrons. 1, 2, 3, 4. It looks like I can link them up in the center. And now I've got 4 hydrogen, and we try to make these molecules as symmetrical or evenly distributed as possible. So we'll go 2 hydrogen on each carbon. It doesn't matter where you put them. So I don't know, maybe I'll put them on the top and on the side. And then I can link those up with single bonds. Hydrogen 1, hydrogen 2. Cool. Okay, so now a piece of cake. It looks like each carbon needs 1 more bond, so we can link them up with a double bond. You don't have to memorize like which molecules have single bonds, double bonds, triple bonds. The triple bonds and the double bonds will usually come to you as you start sketching the structure. Now, if you're really good at this and you wanted to do something like carbon, double bond, carbon, that's totally fine. Everybody will know what you mean by either of those structures. And again, you could put the hydrogens in any position. You could put them on the top and the bottom or however you want. As long as you show that they're single bonded hydrogens and a double bonded carbon. Okay, so let's look at the bonding on those carbons. All of the electrons on carbon are bonded. There's no extra lone pairs. Each carbon has 3 bonding regions. If I look at, let's say this first carbon, there's a pair of bonding electrons to each hydrogen. And then this double bond to the other carbon is still considered 1 bonding region. There are 3 regions of negative electrons on that carbon. Those 3 regions of negative electrons will all repel. And if I think about Vesper theory, they'll want to orient themselves as far apart as possible. So the furthest that I could put those 3 regions of electrons around each carbon would be 120 degrees, right? So we're looking at the trigonal planar shape. Now, sometimes in first year chem you draw these Lewis structures and people will ask me, well, what's the geometry of C2H4? Well, we really wouldn't give it a overall molecular geometry. Instead, we would say the geometry of each carbon is trigonal planar. And often what they'll do is number them. They might have like carbon 1, carbon 2. And so on an AP question, they might say like, what is the geometry of carbon number 1? And then I'd look at the carbon and say there are 3 regions of electrons. And remember that a double bond counts as 1 region of electrons. So those 3 regions still want to repel as far apart as possible. It doesn't matter if those electron regions are single bonds, double bonds, or triple bonds. Okay, so now in real life, this might look a little different. It might look a little bit more maybe like this. Carbon, let's just do the quick double bond, and then these hydrogens will come off at 120 degree bond angles to show that it is really a trigonal planar shape on each carbon. So each of these angles would be 120 degrees. You don't have to draw it like that. If you drew the structure like that first one that we did with the dots, totally fine. That might be the first part of a multi-step free response question. Draw the Lewis structure. Maybe then another question would say, what's the geometry of the carbon? What's the bond angle around the carbon? That's when I would think in my head, trigonal planar, 120 degrees. But I don't have to draw my structure to the exact shape or bond angles. Okay, so now let's get into this hybridization piece. Each carbon needs 3 equal energy bonding regions. So we're going to hybridize 3 orbitals. So remember how like the first 3 orbitals might be like the S and 2 of the P's. Last time when we did Sp2 hybridization, we hybridized the S and all 3 of the P's. But that gave us that tetrahedral structure where there were 4 bonding regions. We don't need that. Each carbon only needs 3 bonding regions. So we're just going to hybridize 3 of the original atomic orbitals on carbon. So these might be like the atomic orbitals. Unhybridized. The spherical S, and then we'll take 2 of the P orbitals. We'll hybridize those atomic orbitals to get these 3 equal energy hybrid orbitals. And remember, we kind of said this whole idea of hybrid orbitals, this only comes into play when we're talking about bonding. For bonding purposes. And when we hybridize, this is brilliant, 1 s orbital and 2 p orbitals, the product is called an sp2 hybrid orbital. Wow, isn't that brilliant? There they are. Okay, so that gives me the 3 bonding regions around the carbon. Okay, so let's take a little different look at this. In the original carbon atom, an isolated carbon atom, we would have those 4 valence electrons kind of distributed as 1, 2, 3, 4. But for bonding purposes, we need to show that there can be 3 regions of bonding around that carbon. So we're going to hybridize those first 3 orbitals. And we'll put 1 electron in each. 1, 2, 3. And now here's maybe where the mystery that you've been thinking in your head gets solved. Hey, wait a second. There's 1 more p orbital out there, right? Where's that extra 3rd p orbital go? Oh, it's still there. We're going to put the 4th valence electron in that extra orbital. So these guys are the hybrids. We're only going to hybridize 3 orbitals because we need 3 bonding regions. We need a region for that double bond, and then we need a region for those single bonded hydrogens. The 4th orbital, that extra p, is just unhybridized. It's just like a normal p orbital. I really, really like this picture down here. It's kind of hard to follow in your study guide because it's not colored, but it is in your textbook. I think this gives a good visual of what's really happening around the carbon. So we're going to have those 3 hybrid orbitals at 120-degree bond angles. So that's kind of what they're trying to show with these green orbitals. These guys around the center are those hybrid orbitals with the 120-degree bond angles. The extra p orbital is still there. It looks just like any other p orbital would. So, here's kind of a normal looking p orbital. That's what they're trying to show in blue. And you kind of tell, and they're trying to draw this like in 3 dimensions a little bit. It's there. That extra p orbital is there, and it looks just like a normal, dumbbell-shaped p orbital. So here's where we're going to put carbon's 4 valence electrons. Oh, let's see here. 1 of them in each of the hybrids at 120 degrees, and then the 4th goes in the extra p orbital, the normal-shaped p orbital. Crazy, huh? Okay, so let's look at carbon. Here's the carbon. Something called sigma bonding. Sigma bonding is when bonds are created when orbitals overlap end to end. Like the lobes of the orbitals are kind of like facing each other. Here are the sigma bonds in this ethylene molecule, C2H4. And when we overlap the orbitals, again, that's where we have this covalent bond, right? Okay, so these are those hybrids, the Sp2 hybrids. And then here's one of them on a particular carbon. Let's say we just look at this first carbon. In green, we've got the 3 hybrid orbitals. 2 of them are going to overlap with the 1s orbital of hydrogen. And again, hydrogen doesn't have a hybrid orbital because he only has 1 orbital available. So we're not going to hybridize if we only have 1 orbital. So can you kind of tell that they're trying to show in here that these electrons are now paired together, spinning opposite? So I overlap with hydrogens, 1s. And that's why those arrows are pointing in opposite directions. When we overlap end to end like this, we form a covalent bond. And more specifically, we can call it a sigma bond. When orbitals overlap end to end. The same thing happens on the other carbon. 2 of the hybrids will overlap with the 1s orbital of hydrogen. Then in the center, the 3rd sp2 orbitals will again kind of overlap with each other. And then we'll share 2 electrons, boom, right in the center like this. Okay, so this is good stuff, right? Sigma bonding, when the orbitals overlap end to end, real common. In the next video, we need to take care of that extra p orbital, right? So far, I hope that this makes sense. And you really have to put on your visual thinking cap to visualize these orbitals. You have to visualize the correct angles, and then visualize the orbitals kind of overlapping to share electrons. So here we've taken care of the hybrid orbitals of each carbon overlapping with the hydrogen to form the single bond, and then those extra hybrids in the center, the 3rd sp2 hybrid of each carbon, they'll also overlap to share 2 electrons.